So a rectangular sheet of paper is folded so that one
Yeah.
corner lies on top of the corner diagonally opposite.
Yeah.
What does that mean though? Okay, can someone explain to me what that means? They have a rectangular sheet of paper, yeah? So one
Diagonally
corner
opposite.
lies on top of the corner diagonally opposite. So this corner, yeah,
Yeah.
lies here.
Yeah.
Is that what we're doing?
Mm. Yeah.
Okay, yeah. Okay. The resulting shape is a pentagon. Okay. Yeah, so this is the first step. We're trying to understand the problem. Yeah.
Yeah.
Okay, now we got some condition. The resulting shape is a pentagon whose area is 20% one sheet thick and 80% two sheets thick. I guess that makes sense, yeah?
Yeah.
So some of it's like folded on top of some paper and some of it's not on top of anything,
Yeah.
right? Determine the ratio of the two sides of the original sheet of paper. So the length to the width. So if this was like the width, this was the length.
Yeah.
We want like the ratio
Yeah. Of them.
length over width, yeah? Yeah, I think this is a nice little problem for us because it's geometry, but it's like it doesn't really need any special things in geometry, you know what I'm
Yeah.
saying? So
Okay.
this is like, you know, this could be an AIMO problem, like one of the maybe middle to later ones. So I guess a lot of you have all got pieces of paper and try to fold them, yeah?
Yeah. That's what I'm doing.
Yeah, that's a good start, I guess. So it's geometry, there's a lot of experimenting. So this folding the paper might be like akin to drawing a diagram. Okay, has anyone noticed anything about the folding? It's kind of like a symmetry, right? Is that what you're saying? So like when you fold it, the two flaps which are only one single side of paper, one sheet of paper is really like 10%, 10%, and they're symmetrical, right? Okay, I mean, you could say stuff like it's a right angle triangle, yeah? Um, okay, so one thing I guess you could notice is, look, if you look at the piece of paper, right? Your piece
Yeah.
of paper,
Yeah.
there's just like there's like literally a huge glaring fold line, right? There's like a line that kind of goes like this, right? That folds across this line, yeah? How are the triangles related to this line? Well, the triangles, the line hits one of the vertices of the triangle, right? So like
Yeah.
this is like one of the vertices of the triangle, and this is the other one, right? Now that I guess I drew your attention to this line. Um, maybe I can also. Can you tell me more about this line and these triangles and stuff like this? I guess this is the parallelogram that Sunny was talking about. It's like that, right?
Yeah.
I'll give you a couple of minutes to think about it, but I want you to tell me what you notice about these lines.
Wait, there's four triangles, like there's two triangles on the outside and then two triangles inside the parallelogram.
Okay, yeah. Um, okay, but if you're going to talk about the four triangles, what else could you say? And so, for example, how are the triangles related to each other? Um, Sunny mentioned something about a parallelogram before, yeah?
Yeah.
What do you know about a parallelogram? Okay, so if you have a parallelogram, Yeah, this all goes on to, again, you have a parallelogram. You know the diagonals bisect
Yeah.
each other? Okay, wait, so let me ask you, do you know what like a relation, what could be a possible relationship between triangle 1 and 4? Okay, so they're both right angled, we know that, right?
Yeah.
Yeah, because on a rectangle they're 90 degrees, right?
Yeah.
But you also have in a parallelogram, like, the opposite sides are equal, right?
Yeah.
And so the opposite sides being equal is equivalent to being a parallelogram, right?
Yeah.
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 So actually, the thing that Sonny saw that this is a parallelogram, right? You can actually
Yeah.
prove it,
Yeah. Because like you can
because,
see.
well, at least you suspect it strongly to be true, right?
Yeah.
Because you have this side, which is likely to be equal to this side by the symmetry, right?
Yeah.
You have that side that's likely to be equal to that side by the symmetry, right?
Yeah. Yeah.
Because basically the idea is, can you see triangle 1 and 4 are basically the same, yeah?
Yeah.
See what I'm saying? And triangle 2 and 3 are basically the same, yeah? Okay, but basically here we have two pairs of congruent triangles, yeah?
Yeah.
So we have the two blue ones and the two right-angled ones. The 1
Yeah.
and 4 and 2 and 3, okay?
Yeah.
So can someone explain to me why 1 and 4 are congruent? Okay, so they're both right-angled, yeah? And they both have one of the length, the long side here is all both the width of the rectangle, right?
Yeah.
So they're equal, right?
Yeah.
Okay, and then this folding line is unique. Like if the line were to do something else, the the point would no longer fold.
Yeah.
Does that make sense?
Yeah.
Hmm. Actually, I might want to revisit also our need claim is it actually equilateral triangle? Okay, because that's I feel like we weren't up to that idea yet, but now that I'm thinking about it, is it plausible that it's actually equilateral triangle? So are 2 and 3 actually equilateral?
Maybe.
Yeah. Hmm. Yeah, see, for example, like in a parallelogram, like we know these sides are like parallel, right? Yeah. Okay, and then somehow we can conclude that the opposite sides have the same length. Yeah. Okay,
Yeah.
so one way of showing that is you can show, if you look at this triangle here, right?
Yeah.
And then you can look at this triangle here. Yeah. Okay, and because they're parallel, okay, we know that this angle is equal to this angle, right?
Yeah.
Because it's alternate angles and parallel lines. You all learned this in year 7, right?
Yeah.
Okay, and then um, we have actually we can maybe break it up into these triangles, yeah? So we have this angle is also equal to this angle, yeah?
Yeah.
Okay, and then so we basically have all three angles. If you have two angles equal, three angles are equal because it's it add up to 180, right? So we basically have two triangles where all the angles are equal, yeah? But can you see they also have a common side in the middle, so that side has to have the same length, yeah?
Yeah.
So then we have this AAS congruence, okay? That means these two triangles are congruent, okay? And once we know they're congruent, we can conclude the corresponding sides are equal. So the one opposite the dotted angle is this one, and that one, those lengths are equal now, yeah? And this one is opposite the circle, and this one's opposite the open circle. They're equal, see? So we're able to use the definition to prove that the opposite sides are equal. Okay, so we're back to the question, are these triangles equilateral? And maybe like a broader question is like, what does it mean to fold, you know? What's the nature of that line? We know that line's unique, okay? It can't be any other line, but why is it unique? What's the relationship between the line and the points? So this is the longer side of the triangle, yeah? Yeah. Can you see when that folds, it folds into this side here, right? When you fold it. So those sides actually equal. Does that make sense?
Yeah.
So when you fold it, this side goes to that side, so they're equal. And it's the same for the other side, okay?
Okay.
So this side here folds to this side.
Yeah.
Does that make sense?
Yeah.
And so if it was a parallelogram, then now it's a rhombus, okay?
Yeah. Okay.
Okay, good. So it's not necessarily equilateral, and we know it's, in this case, for A4 paper at least, it's definitely not equilateral, yeah? And so
Yeah.
this is where, like, Sonny was correct. Like, if it was equilateral, it could just be lucky, right? There might be
Yeah.
some paper that gives you equilateral, but we definitely know it's isosceles no matter what the paper, right?
Yeah.
Okay. So we know it's isosceles. So we actually know quite a lot about this, okay? So what do we know about, like, this length here?
Are they both equal?
Yes, but what else can we figure out about those lengths? Like you might be confused if you can't find the exact length, right?
Yeah.
But I think we're not really after the exact length right now. We just want to understand how the length's related to the problem, yeah?
Yeah.
So for example, we know that the area is 20%. So you gotta be a bit careful here because you can't just say like, because the area of these two triangles is just length times width, right?
Yeah.
And that's 20% of the area of the one of the pentagon, right?
Yeah.
So if it was 20% of the area of the rectangle, then you actually know that this is like 20% of the length of the rectangle, right?
Yeah.
Which basically tells you a lot, yeah?
Yeah.
Okay. And then you know that's 80%. But it's not the rectangle, it's the pentagon, right?
Yeah.
So, but it's not that different, because if you have a relationship between the area of the pentagon and the area of the rectangle, then you just as well get this length as well. Yeah?
Yeah.
That makes so so actually what you notice is you can actually just find this length if you know enough information about the shape. Yeah?
Yeah.
Okay. Okay, but we're on the moment we're actually on the precipice of a major realization, so I was kind of reluctant to take a detour, but maybe this also uh, so if we get back to the equilateral isosceles triangles, yeah?
Yeah.
Okay, what now if we assume it's isosceles, okay, what can we get from that? Like what happens if I draw I mean this is a pivotal little joining because this is where the 2 points are actually folding, right?
Yeah.
What if I draw that line? What can you tell me about that line?
That line bisects the other line.
Okay, very good. So this line bisects that line, yeah? We know like these lengths are all the same, right?
Yeah.
So like if you have an isosceles triangle, right?
Yeah.
And you draw it to the midpoint down here, yeah?
Yeah.
What can you tell me about this line?
That it cuts the two triangles in, and then like the two triangles become right angle triangles.
Yeah, they're 90 degrees, yeah?
Yeah.
So this line is an altitude, yeah? Does
Yeah.
that make sense? And the way it's proved, see, if you look at the proof, it's like sides are equal, yeah?
Yeah.
Sides are equal,
Yeah.
and there's a common side, yeah? And this is SSS. That makes sense? So that
Yeah.
means these two angles are equal, but they also add up to 180, right?
Yeah.
They're they're on a straight line.
Yeah.
So if they're equal and add up to 180, they gotta both be 90. Okay, you guys know what a kite is? You've heard that the diagonals intersect at 90 degrees. Well, that's also what's happening here, right? Okay. Okay, and what else do we need to what else can we mark in here? Yes, I'm just asking something basic. So can you see that these lines are also equal in length, right? Does
Yeah.
that make sense?
Yeah.
So that's all like so now we put like that's obvious. We know that, right?
Yeah.
Okay. But what I want you to see, can you see like once we put all this onto the diagram, okay? Can you
Okay.
see that we actually can understand completely what it means to fold along that line? So that's what I want you to think about for the next few minutes. Okay, so I don't think you actually need to know this terminology to solve the problem, okay? But I think we want to learn something um good takeaway from this. It's funny, like understanding the problem is kind of like theory building. You know, we're trying to build in the theory of the problem. So have you guys heard of this thing called perpendicular bisector? Have you heard of that thing? Huh? So
No.
so basically a perpendicular bisector, it's literally what the name says, okay? So if you have 2 points, okay, yeah, and you join them, there's a line that's perpendicular the and bisects, yeah, the interval. This is called the perpendicular bisector. Yeah. So what a perpendicular bisector is, it's literally all the points which are the same distance from these 2 points. Okay, and they form a line right down the middle. That's a very fundamental piece of geometry. And so what we've just understood essentially is that the fold line, there can only be one fold line, right? Is the perpendicular bisector of the 2 points. Okay. And in that sense, if we know about perpendicular bisector, then that kind of proves there's only one fold line as well. Okay, because there's only one perpendicular bisector. All right. um, and that really makes sense. Okay, if you think about what folding means. Okay, this will actually explain to you what folding means. Because what are you really doing when you're folding a point, right? You're literally reflecting it across the line, right? That makes sense? So if you're reflecting it, the distance from the line should be equal to the distance on the other side, right? And it's a right angles because you're reflecting it like across the line, right? You're not reflecting it at a weird angle. So folding across the line is literally reflecting across the line. Okay? That tells you a lot. Um, So, for example, like this angle should be equal. We already know that this angle should be equal to that one. When you reflect it, this length should end up like that. You know what I mean? Okay. So, some people say, well, this would be contributing to solving the problem, but I would say this is still understanding the problem. Okay. But the beauty of understanding the problem is the more you understand the problem, the easier it is to solve the problem once you're trying to cash out. Okay. So here we have a complete understanding of the problem. All right. So now the question is, how do we use our complete understanding to acquire the answer they're asking for, right? So at this very point, like this problem would be super easy using coordinates right now because you know exactly where everything is, okay?
Yeah.
So maybe that could be a good exercise for some people who know about coordinates. But we're not going to use coordinates right now because it's like the beginning, yeah?
Yeah.
But this problem is essentially done with coordinates, um, if you know what the fold line is, yeah? Okay, but now that we know it's the perpendicular bisector, essentially we know all these things are symmetric about the line, right? The fold is literally just reflecting it now. We know that, okay? How can we solve the problem now? You know? Do you still remember what the problem is?
Yeah. Like
Yes.
determine the ratio of the two sides of the original sheet of paper.
Yeah. So I guess you might want to recall that little aside that we had when you mentioned this length, right? I mean,
Yeah.
so I guess it suffices to find sort of the relationship between the area of the rectangle and the pentagon. Yeah.
Yeah.
Yeah, like how is the area of the rectangle related to the area of the pentagon? You know? Yeah, so what's the area of the pentagon?
I'm not too sure.
No, we can figure it out, yeah?
Yeah.
Just think about what we've done. What happens when you fold? Like, look at our diagram. How do we get the pentagon?
By folding like the corner to the other corner. Like
Yeah,
diagonal.
so what's the area of the pentagon related to the areas of these things here? Okay, that's what I want to know. So, we have the area of a rectangle here, right?
Yeah.
And then we fold it and we get the area of a pentagon, yeah?
Yeah.
What's the relationship between those two areas? Or what is a relationship between those two areas? Okay? We have four triangles. Yep. So the area of the rectangle is the sum of the areas of the four triangles. Yes? That's
Yeah.
obvious. Yeah. Okay, so I want what the relationship is for the pentagon. But what Sonny was saying is that the area of the pentagon is the same area as the rectangle, but minus this fat triangle, right?
Yeah. Oh yeah.
Yeah? And that gets folded up. That makes sense?
Yeah.
So the three triangles gives you the pentagon, the four triangles give you the rectangle. Yeah? Okay,
Yeah.
now what else do we know based on the question about the area? This one is 80%, and these two are 20% of what? Of the pentagon, okay? It makes a difference. So so these triangles are 20% of um the pentagon, and this is 80%. Yeah? So what does that tell us? And we know that these are 20% of the pentagon, yeah?
Yeah.
This is 80%, yeah?
Yeah.
So what does that mean? See? You know, what do you have here? You have literally six triangles, right? Yeah? But all four of these triangles here are congruent, yeah? And the area consists of exactly two types of triangles, right? So it's that one and this one. Okay, think about the relationship between them. Yeah. Like what's the relationship between the big triangle and the edge triangle? And it's a very basic relationship. I'm not asking you for anything crazy. Okay, so this is basically what Sunny is saying is right, okay? But you said the wrong numbers, okay? So like if this is 20%, okay, and this is 10%, right? This is 10%, right? And these are 80%, so this is 40%. This is 40%, right?
Yeah.
So what's the relationship between the two areas? So I deliberately didn't say areas because I wanted you to think about that's what we're looking for, right? If I said areas, I might give it away too much. Yeah, one is 4 times the other one, right? Does that make sense?
Yeah.
So now we can forget about the pentagon now, right? So this is a pure simplification, do you understand? So then the information given to us by the pentagon thing is really just telling us this is like area, like this area of this is like A, right? And the area of this is like 4A. That makes sense?
Yeah.
Okay. And these are the same, right?
Yeah.
Okay, now what do we do? So we'd
Not
originally wanted to find like this length, for example. Do we have that now? This is if this was width and this was length, right? Of the whole thing. Do we have this length? And so there's 18 A's altogether, right? And 2 A's is a ninth of 18, right? And the width is the same, so it should be a ninth of the area, a ninth of the length. Yeah, this is a ninth one on. This is L on 9. Yeah. And so you might want to notice that the areas are now pretty consistent if you just do some basic, like for example, if you do this area of this big triangle here, that's 8A, right? Which is 8 times little a, and so this length here should be 8 times the length of this. Yeah, the height's the same. The height's the width. Yeah. Or like if you cut across this trapezium, it's half the area. Okay, so the areas are pretty consistent. Okay, we just want a relationship between L and W. Okay, so for example, this is L on 8L on 9, right? Yeah. All right, you have any ideas? Okay, so remember we just need one relationship between L and W. Yeah. Can you
yeah.
see where we might get that? I mean, for example, we know that this is 8L on 9, right?
Yeah.
Yeah. Can you see that this is also 8L on 9 here?
Yeah, and then like
The
that's also
same, right?
the other one is also like the other two are also the same.
Yeah. But let's just focus on this, yeah?
Yeah.
You see how that gives you a relationship between L and W? This is a right angle triangle, okay?
Yeah.
So Sunny said it, but not very loudly. It's Pythagoras, yeah?
Yeah.
See? That's very good. Alright, see if you can finish it off from here, okay?
Alright, so like should I like solve the Pythagoras theorem then?
Yeah, of course. And there we go. 8L on 9 squared. Right? Yeah. So you don't actually have to square the nines. So at the moment, what you essentially have is you have 64, right? So it's really just it's 64, and then it's like L over 9 squared, right? Equals L over 9 squared plus W squared. You know? You don't need to square the 9. Okay. Um, Ani, have you done this? What do you do next?
Um, but I did it a different way, but I think like I did it a different way, but I think like this is like a different way. But I'll just like to listen to what you're doing.
Okay, yeah.
Yeah,
So here, yeah. So sometimes, yeah. So you got 63, right?
yeah,
63 11 9 squared equals w squared. Yeah.
yeah.
Okay. Then what did you do?
Oh, and then I put the square root of like the thing on the other side, like so w is equal to the square root of like 63 times L over 9 in brackets square.
Yeah. So you took the square root of both sides. Is that what you did?
Yeah,
Okay, so then w, and then so usually it's plus minus, but we know everything's positive. Yeah.
yeah,
So that's something that's going to come back to haunt you if you don't take care of that.
yeah,
So you get root 63 L over 9. Yeah?
yeah.
Okay, then what did you do?
Um, and then I did wait, and then I put it as 9, like square root of 9 times square root of 7 L over 9, like times L over 9.
Yep, okay, that's good. The square root of 9 times the square root of 7 times L over 9. Yep.
Yeah, and then like I didn't know what to do after that though.
Oh, I mean, we're basically at the answer. So what's the question asking you, remember?
The ratio.
Yeah, so Joshua, what do you do from here, you know? I mean, one obvious thing is the square root of 9 is 3, right? So the square root of 9 is 3,
Yeah,
and the 3 cancels with this to get 3, right? That makes sense?
yeah,
So then you can divide both sides by L or divide both sides by W. Um, and get root 7 over 3 equals W over L, right?
yeah,
We've solved the problem now, yes?
yeah. I understand now.
Okay, good. So the ratio from width to length is root 7 on 3.
Yeah. Okay.
Yeah, so root 7 is less than 3, yeah? We need that
Yeah.
for W needs to be less than L, yeah?
Yeah.
Okay. Yeah, so that's a complete problem. Well done. Okay, so in summary, I mean, obviously the problem like doesn't actually necessarily take this long. Once you get better at it, it's kind of you can probably get a lot of this right away. Yeah. But what I've kind of shown you is like a general process of investigating a problem. You understand? Like
Yeah.
most of the stuff you do at school and other people teach you, they're just kind of it's more just memorizing the solution. You know what I'm saying? But you
Yeah.
can't memorize a solution that you don't have. Okay, this is more like about creating the solution. Does that
Okay.
make sense?
Yeah.
So this process it can solve very easy problems. It can solve, I guess this would be more like a easy medium problem, okay? But the same process can solve even unsolved problems in mathematics. Does that make sense?
Yeah.
It's not like it's not like the unsolved problems are any more like they might take longer to do, right? Or it might
Yeah.
take new ideas, observations along the way, but we're still investigating.
Understand.
Yeah. So this approach, you can use it to solve any problem. Yeah.
Yeah. Yeah.
And notice we didn't assume you knew anything, right? But we kind of there's some things we'd like to remember that we learned along the way to use next time. So like perpendicular bisector, isosceles, congruent, similar, those kind of things, they'll come up a lot. So we want to kind of, we want to not have to rediscover them every time. Yeah. So we
Yeah.
kind of try to memorize them. But at the start, it's the memory is not as good because at the start your mind is not as good, so you memorize things with low quality. Yeah.
Yeah.
okay? Because you don't really understand them as well. But later on, when your mind gets better, you get more logical, you've had some more experience, and your brain literally grows, okay?
Yeah.
The quality of your understanding and knowledge will also improve, okay? And then you
Yeah.
can memorize
Okay.
things with more confidence.